Good morning. This video is intended for anybody that's working from a distance on part 2 of lab 1 on electric charge. Assuming that you've never done, or it's been a long time since you've done video analysis in LoggerPro. If that's you, then hopefully this video will help you walk through that piece of the experiment. So the experiment that we're actually studying in part 2 is captured on video elsewhere. I'm trying to remember if this was at MIT or RIT, one of those institutions. And it consists of a light sphere hanging from a thread from the ceiling, and we'll play the video here and just watch what happens. So somebody's bringing in an identical sphere that's connected to a stick, and note that as the sphere on the stick approaches, the sphere that's hanging from a thread is deflected away. And this is due to the fact that both of these spheres are electrically charged, and they both must be similarly electrically charged, either both positive or both negative, because they're repelling each other. So the question we're trying to address in this part of the experiment is, how does the electrical force between these two objects depend on the distance between those two charged objects? So that's the video that we're going to do, and to do this analysis we're going to work in LoggerPro, but the two variables that we're going to need to put into LoggerPro can't be directly measured. That is, we need, if you think about the question, we need the force between these two things. So we need an expression for the electrical force on at least one of them, and then by Newton's third law that would be equal to the electrical force on the other. And we need the distance between them. Well, the distance between them is going to be pretty easy to do. We're going to mark the positions of each of these spheres in each frame of the video, and then we can calculate the difference between them. Actually, LoggerPro will do that calculation for us, and we'll have that column of data. But the electrical force is a tad bit trickier. So we're going to switch over and work out the details of that here with the old trusty pencil and paper method. So I'm going to think about that hanging sphere and just draw a little diagram of that hanging sphere at some angle relative to the equilibrium direction where it was hanging straight down, something like that. And then I'm going to draw a free body diagram of that same thing. And you'll recall from your Physics 1 that when you draw a free body diagram, well, people have slightly different methods of doing that, but I'm going to draw an outline of the object and then identify the three forces that are on that object. So there is a gravitational force down. The Earth is pulling on that object in the downward direction. I'm going to label that F grav. You may have learned a different labeling notation in your Physics 1, and if you have and you are more comfortable with yours, feel free to stick with your system. There's a string pulling, so there is a tension force up at an angle, and I'm going to call that my force from the string. And there's an electrostatic force, or an electrical force, that is directed directly away because the prod was pushing and this sphere was swinging away. So I'm going to call that one F electric. And those are the three forces that are on that hanging sphere. And since two of them are in the horizontal and vertical directions, it's going to be convenient when we do our analysis here to go ahead and make a coordinate system that y is up, x is to the right, the standard Cartesian coordinate system that we frequently made use of in Physics 1. Okay, so there's my forces, and so I need to get an expression for the electrical force. Well, I don't know directly how to calculate the electrical force, but here's the argument. If this sphere is in excuse me, is in equilibrium, then this electrical force must balance with the component of the string force that is in the x direction. So hopefully you recall breaking forces into x and y components when you did your Physics 1 work. And similarly, this gravitational force is going to be equal to the y component of the string force. So if I can break that string force into x and y components, I can write some statements of equality and actually ultimately have an expression for calculating the size of the electrical force. All right, so how do we do that? Well, let's see. Maybe we need to see if that's better on the video there. A little bit bigger. Okay, so I'm going to apply Newton's second law now and say, let's add up all of the forces that are in the x direction. And in general, of course, that equals the mass times the acceleration in the x direction. But if we think about this at an instant where this sphere is momentarily at rest, at equilibrium, this is going to be 0. And so what that says is that the electrical force, which is in the positive x direction, minus the x component of the string force, which is in the negative x direction, must equal 0. Or the electrical force equals the string force in the x direction, which, by the way, equals the overall string force times the sine of theta. Now, how do I know that's the sine of theta? Well, if we look back at our original diagram where theta is the angle that the string makes with the vertical, then on our free body diagram, this is also theta right here. And if this angle is theta, that means the vertical component of the force here is going to be the cosine component because it's the adjacent side. And then this horizontal component, if I moved it up here, would be the opposite side in this right triangle. So it gets the sine in its component. All right, let's do similar analysis in the y. Sum of the forces in the y is also equal to mass times acceleration in the y, but again, at equilibrium, that's 0. So that says that the string force in the y minus the gravitational force equals 0. Or we can write that the gravitational force is equal to the string force in the y direction, which is equal to, the light's going off in the classroom because I'm not moving around, which is equal to the string force times the cosine of the angle. And those are going to be the two pieces we're going to put together for an expression to solve for the electrical force. So let's call this number 1. Let's call this one number 2. And then I'm going to actually pull one of my favorite tricks from algebra, which is divide equation 1 by equation 2. There's other ways to do this, so if you don't like this, you can do the algebra your own way. F electrical equals the string force times the sine of theta, and the gravitational force equals the string force times the cosine of theta. And the reason I wanted to divide those is string force cancels then, and I'm left with sine over cosine here. And you may recall from some trigonometry of the distant past, sine over cosine is tangent. So now I have the electrical force over the gravitational force equals the tangent of theta. Or the electrical force equals the gravitational force times the tangent of theta. And the electrical force, we don't know what it is, but the gravitational force, we can figure that out if we know the mass of the sphere, and we do, it's labeled in the video, and we know the local gravitational constant, sometimes called the acceleration due to gravity, little g, which we also know. We need to know the angle as well, and we don't know the angle, but if we go back and look at our original diagram right here, let's go ahead and complete that right triangle on the hanging sphere. So how do you get the tangent of this angle? Well, the tangent of this angle is the ratio of the opposite side, so that's over here. So I'm going to call that x, which is how far this hanging sphere swings from the equilibrium position. And then I need the adjacent side of this right triangle, which is right here. That's a little bit trickier to get, but we are told what the length of this string is in the video. So I'm just going to label it arbitrarily L. And then recall from the Pythagorean theorem that you learned in high school math that when you have a right triangle, the square of one of those sides, a squared plus b squared equals c squared. Well, in this case, it's going to be x squared plus unknown squared equals L squared, which means the unknown side is going to be L squared minus x squared, and then the square root of that. All right, what are we doing with that? Well, we're going back to our expression for electrical force to get it in the final form. The electrical force equals, and I'm going to go ahead and replace force of gravity with the mass of the sphere times g, the acceleration due to gravity, and then tangent of theta, the ratio of the opposite side, so that's x, over the adjacent side, square root of L squared minus x squared. Just like you would have guessed, right? No, I'm joking there. Almost nobody just guesses this without going through all of the derivation work for this expression. All right, we're going to need that for our work in LoggerPro, so that's what I'm going to switch over to now in the video, if I can get this to work. All right. So here's LoggerPro, and LoggerPro you may have used in Physics 1, connect probeware, take some data in there, but you can also do video analysis in LoggerPro for experiments that are, for one reason or another, difficult to do in the lab you happen to be in. Well, if you're taking this online, number one, that's a difficult experiment to do in the lab that you're in. Secondly, electrostatics experiments are notoriously finicky. It looks simple in that video, but it's actually pretty challenging to get those two spheres to both be charged, to hold the charge in the environment they are without having it leak off into the air, and to conduct the experiment they did. So we're grateful for their work, and we're going to use their video to do our work. So I'm going to go through this fairly quickly in LoggerPro. I would encourage you, as you're watching this presentation, to open up a copy of LoggerPro of your own and go through step by step with what I'm doing here, and you can pause the video at any time to allow you to catch up. The other note I'll say is that one of the two labs in Unit 1 must be selected for writing up your lab report for the electrostatics unit. And so this part 2 of Experiment 1 is one of those experiments that you can select. If you don't want to write up this one as an experiment, there will be a lab coming down the road about capacitance that can be selected as well. All right, so my first step, once I have LoggerPro open, and there's no device connected to it, is to insert that movie. So I go to the Insert Movie menu, and then it's a bit of a rabbit hole, but this is in the lab handout how we find our way to this movie. So in the LoggerPro folder, there is an Experiments folder. Down there is Additional Physics. Within Additional Physics is a curriculum package called Real-Time Physics. In real-time physics, there's electricity and magnetism, and in electricity and magnetism, finally, we find this movie called Coulomb.mp4, and I'm going to select that, and it opens up the video. Now, I already have the video open on my desktop in QuickTime, but I need the video to be opened up in LoggerPro in order to do the analysis in LoggerPro. So here's what the video looks like in mine, and again, I can play this, and this looks exactly like it did when I played it in the QuickTime player. Probe is approaching the hanging sphere. So I need to know what the position of each of those spheres is in each frame of the video. I'm going to go back to the first frame of the video. I'm actually going to go to the second frame of the video, though in the my counter at least it calls this frame 1. This is the first one where both objects are visible. In the lower right corner of the video is a button to enable or disable the video analysis tools. I'm going to click that and open up, and you'll notice a few buttons open up here of video analysis tools. And the first one I'm going to select is the one that looks like a dot in the crosshairs. And selecting that now, I can click and mark the position of an object. And you have to choose a position that is going to be easy to find in each frame. I'm going to go for, as best as possible, the center of each of these spheres. But as long as you're consistent with the location you're marking, it doesn't really matter which location you pick. So I'm going to pick that and click. And when I click, it leaves a dot in the center of that sphere. If I can get my, yeah, there we go. And even though it's kind of imperceptible here, it advances the video to the next frame. And that's just for ease of marking, because I can then click again in the next frame and mark what I believe to be the center of this hanging sphere. And so I'm going to keep doing that through the, I believe, 18 frames of the video. And you'll notice that while you're doing this, it's generating some data in the window behind me. It's making a graph. We'll talk about those momentarily. All right. Probably not the best job in the world, but I got pretty close in most of those. All right, now I have the positions of that sphere marked, but I need to now mark the positions of the other sphere. And so I'm going to jump back to the first part of the video and pardon me, go down to this sixth button, which allows me to add a point series. So I'm going to select the Add Point Series. And what this does, if I pick that again, is note that the original ones I've marked, LoggerPro called X and Y, their coordinates in the X and Y coordinate system that we're using. Well, now I'm marking one called X2 and Y2. And I could actually jump back here at any time and switch between them, but I've already marked all the positions of the object I'm calling Object 1. So we are going to do the same kind of thing. And even, at least in mine, it never shows up as crosshairs for frame 1, but I click and it still makes that dot there. So again, my goal here is marking the center of the dot, or the center of the I call it the prod sphere, in each of these frames. Didn't care for that one. If you don't like it, you can select the arrow and delete. So you just click on the dot. It's a little bit hard to do, and hit delete. Now I'm going to remark that one. All right, now I've selected what I believe to be the center position of those spheres in each of the frames of the video, and so you'll notice behind me LoggerPro has been making this graph, which doesn't really have any meaning for our experiment, but it's both the horizontal and vertical positions of both spheres marked as a function of time. That's not the graph we want to end up with, but we will want a graph out of our results. We need to do a couple of other pieces of setup work here, though. Recall that in our derivation of the expression for the electrical force, we called the distance that this hanging sphere swung from its equilibrium position X. And so in order for for the positions that we marked, which are marked with the blue dots here, to actually be x, we need to put the origin at where that sphere originally was. Now, in LoggerPro, if you don't tell LoggerPro where you want the origin to be, the default origin is down here in the lower left-hand corner. So I want to tell LoggerPro that I want to put the origin right at the original position of this hanging sphere. And the way I do that is I select the third icon down in the list, and then again put where I want my origin to be, and I want it to be in the center of this sphere. So I'm going to click there, and there's my new origin, and you may notice off on the left in the data window, LoggerPro recalculates the positions of everything in that window. You can also, if you're doing an experiment where you want to rotate the coordinate system for some reason, grab this yellow dot and do so, but I'm going to leave it alone because I want horizontal and vertical here. The other piece is LoggerPro has no way of knowing what distance anything is in this video frame. And so if you look over on the left, it's actually measuring positions in pixels for those of you that like old video technology here. So I have to tell LoggerPro what that is, and the way I do that is the fourth button down in my video tools, which is to set the scale. And in many of these pre-provided videos, they give you a set length. So down here at the bottom is a meter stick. They've conveniently marked it 1 meter in length. So I click and drag, and when I release, LoggerPro will bring me a pop-up window and asks, how long is that line that you just dragged? In this case, it's 1 meter. But if you know the size of anything in your video frame, you can use that to establish the scale of everything else in the video. That should be everything that we need to do with the video. So I'm going to actually just shrink this video and move it, but not close it out, because in case we need to come back to it for one reason or another. My next focus is going to be to look at this data window that we've generated here. So I'm going to click on that and make it much larger temporarily so that we can see all the columns of data that LoggerPro has generated, most of which we don't need. So you'll note that it automatically stamps the time because it knows what time in the video you're at, and it marks the X and Y positions of both of the spheres that we marked. In addition, it estimates the X and Y speeds of those objects, and again, in certain experiments that may be a useful piece of data but not something we need. So I'm actually going to just get rid of the columns that we don't need, which, by the way, is an optional step. You can leave all these columns in here. It doesn't hurt anything. But I'm going to get rid of the X column by highlighting it and then hitting delete. If I get rid of the Y positions, which we also don't need, we only care about the horizontal position of these spheres, then that is going to get rid of both Y and VY, since VY is calculated off of whatever Y is. And I'm going to get rid of VX. So now I'm down to a place where I have just my X variables, or my X positions rather, for the two objects that are moving, and the time. And I'm going to just go ahead, because why not, and save this. You can save any of these files. They save as CMBL files, and then they reopen up in LoggerPro if you want to work on them later. Okay, so again, what's the original question we're trying to answer? How does the electrical force depend on the distance between the two spheres? Let's go ahead and calculate the distance between the two spheres. I go to my data menu and I choose a new calculated column, and it brings up a menu and says, what do you want this column to calculate? Well, let's call this the distance between spheres. I'm going to give it the short name of R, and that's just because when you actually see this formula in most books, that distance between objects is called R, so let's make that match up. It's going to end up measuring in meters, since both of my positions are measured in meters. And then down here in the expression, in order to figure out the distance between the spheres, I want to take the position of the right-hand sphere, so that is X, and I want to subtract the position of the sphere connected to the prod, that was X2. And when I hit done, LoggerPro calculates all of those positions for me automatically. And notice it starts with the spheres about half a meter apart, and then it goes to the spheres being about 10 centimeters apart by the time I'm done with this video. The other one's a little bit trickier, but recall that we did this expression for the electrostatic force here And so that's the one that we're going to need to code into LoggerPro here. mgx over square root of L squared minus x squared. So if we, let's hide Elmo. Okay, back in LoggerPro, I'm going to make a second calculated column. Again, the data menu, new calculated column. And this one is going to be the electric force between those two spheres. My short name I'm just going to call F-elec. You can give it whatever name you want to there, but the short name is used for these columns when there's not enough space to fit the whole name in there. This is going to come out in units of newtons like other forces do, provided that we code in all of the numbers correctly. All right, down in the expression, we need the mass of the sphere. Well, notice on the video down here, they conveniently told us the mass is 2.93 grams. But if I'm going to calculate something in kilograms, I need that to be in in newtons rather. I need the mass to be in kilograms, so 0.00293 times. Now I need G. I use 9.8 for G. Others use 9.81. It doesn't really matter at this stage which one you use. Times, now X, the horizontal position of that swinging sphere, so that's X right here, divided by, and now we need the square root of L squared minus X squared. Well, L squared is the length of or L rather is the length of the string, and the video tells us that's 2 meters from the ceiling. So there's a couple of ways you can do this. I like the function. So the function for a square root is SQRT. The other option of doing this is enclose everything in parentheses and then raise it to the power of 1/2. But I'm going to use square root, SQRT, and then I do put an open parentheses. L squared, well, L is 2, and 2 squared is 4, so I'm just going to go ahead and directly put in the 4, minus, and then in this variables, I'm choosing again X, the horizontal position of that swinging sphere. To make it squared, I'm using what I call the caret, the little arrow above the 6, so shift 6, squared, close the parentheses, and there we have it. So there is the expression for calculating the electrical force between these two objects. And I hit done, and LoggerPro calculates it for me again, and it looks like, for first glance, a bunch of zeros. That's because these electrical forces are fairly small. If you want to see numbers here, you can double-click on it and go to the options of this tab, options of this column, excuse me, then change it from displaying, say, 3 decimal places to using scientific notation, and then you'll see those numbers times 10 to the whatever, though the computer way of times 10 is to use the capital E. So this is 3.63 times 10 to the negative 6, 3.15 times 10 to the negative 5th, etc. All right. So I don't need my entire data window again. Let's shrink it down to here. And now let's finally go to our graph window. This is where we're going to be displaying the relationship between the electrical force and the distance between spheres. And one of the reasons I like LoggerPro is it's really easy to make graphs in here if we've already done all the other work. If I click on this vertical axis, instead of having X and X2, the positions, I'm going to choose electrical force. On the y-axis, I want force as a function of distance, not of time. So I'm going to click time here and change it to the distance between spheres. And voila, there is the graph that shows that relationship. If you would like, you can, I think, click on those data markers and change it if you are anti-triangle for some reason. You can make those, excuse me, different sizes. But there's the data that shows that as the electrical force, or rather as the distance between spheres increases, the electrical force decreases, or more in line with what we did, as the distance between spheres increases, so you have to read the graph right to left, the electrical force increases. But we're not quite done because we want a model. We want a mathematical relationship between electrical force and the distance between spheres. To accomplish that, again, it's fairly easy because LoggerPro has the tools built in to do this. We go to the Analyze menu and we choose Curve Fit. And here we have to know something about mathematical expressions and which mathematical expression would be the most appropriate here. For example, if I pick proportional, that doesn't look great. Proportional is a linear graph that has to go through 0 and yeah, not going to fit the data very great. I could do a linear relationship, and that's better. At least it has a negative slope, but that is not a fantastic fit. Quadratic fits a little bit better, but we actually discard quadratic because it doesn't make physical sense. Notice that a quadratic makes a parabola. So that would be like saying, well, over my data, I saw that as the distance increased, the force decreased. But I think if I kept increasing distance beyond that, the force would eventually increase, which doesn't at least make physical sense to me. The real expression that we want down here is in the inverse realm. You can try a straight inverse fit, and it fits okay, but a much better fit is something called the inverse square. And you may have run into the inverse square if you did Newton's law of universal gravitation in your Physics 1. This is the exact same format of an equation. I'm going to try that fit and note that it fits very well, like I suspected that it would. Hit OK, and I'm pretty much done. There's one other piece you need to do, and LoggerPro won't do this for you. But I have this expression that says the electrical force equals A, and the A that it gives us here is 1.426 times 10 to the negative fifth. You can decide how much of those digits you want to keep in your model. I'll probably keep 3 digits times 10 to the negative fifth over r squared, and r is the distance between spheres. So I'm going to wrap this up by switching back over to my writing screen and see what we've written there and how you finalize this particular model. So note that now we took our expression for electrical force and we solved for it, but now the model that LoggerPro is giving us for that relationship is that the electrical force equals 1.43 times 10 to the negative fifth over r squared. And the one piece we need is to ask ourselves, what would be the units of this 1.43? Well, I know electrical force is in newtons, so this side must have newtons, and newtons isn't going to come from r squared, so there must be a newton involved in the units there. But r is going to have units. R is the distance between spheres. We measured the positions of the spheres in meters, so r squared is going to have units of meters squared. And I don't want that in my units when I get the electrical force, so I'm going to need a meters squared in that unit as well. And that is, in fact, our final model that we derive from this particular experiment, though I suspect your number up here in the numerator is perhaps slightly different from mine if we didn't mark the exact same position of those spheres as we were doing the exercise. And again, if you choose this lab to write up, then you would describe in your report the process that you just went through. But also there's a couple of extending your model questions. So now, what's the point of this model? Well, the point is it's more general than just the data that I measured. If I know a new distance between these spheres, I should be able to plug that into the model and predict what the electrical force is between them. Or if I know what the electrical force is in between the spheres, I can plug that into the model and predict how far apart those spheres are from one another. And so this is, for all intents and purposes, an equation that accomplishes this. And this is a beginning form of something called Coulomb's law. You'll learn more about Coulomb's law either in the first lecture or in the first reading. All right. Thank you for watching this, and please let me know if you have questions about any of the parts of this experiment that we walked through.